So, welcome to the today's JSON and a special seminar. This is the first time that we are broadcasting this seminar online, and for this special occasion, we have a great scientist joining us to talk about nanomaterials and environment. And it's a great pleasure to have Dr. Khara Grieger. She is a senior researcher in the Genetic Engineering and Society Center of North Carolina State University. She will be an assistant professor in environmental health and risk assessment from this July. And she has a master's degree from DTU in environmental engineering, a master in plant biology and ecology, and a bachelor for zoology from Michigan State University. She received her PhD and her postdoctoral training from Technical University of Denmark, or DTU. She has been a senior environmental research scientist at RTI International in the health and environmental risk analysis. She has been a Duke University scholar. She works on a range of projects related to responsible innovations of emerging technologies, including nanomaterials. And for instance, she studied this societal implications of nanomaterials in the agriculture industry. Another project that she was involved in was sustainable development of nanomaterials for water treatment. She has also been involved in a large European project regarding mitigating the risk of nanomaterials, which is expected from someone that comes from DTU, from Denmark. And I know this topic is very exciting, and I expect that we're going to have a lot of questions. So please keep the questions to yourself, or maybe put it in the chat, and we're gonna address them after the talk is over. So now the floor is yours. I'm gonna remove myself from the screen so that Khara can do the nice presentation. Thank you.
Okay, thank you, Reza. That was a really nice and warm introduction. So thank you all. I hope everybody can hear me okay and see my slides okay. So the title of my talk is called Ensuring Responsible Innovation of Engineered Nanomaterials. And what I'd like to talk with you about today is just to give you another quick background on who I am. I know Reza already mentioned a few things, but I'd like to just recap on who I am, where I'm coming from, give a quick recap on what engineered nanomaterials are for those of you who aren't totally familiar with that. I realize this will be a recorded webinar. So after that, we'll talk about responsible development of nanomaterials and why that's important. Touching briefly on some of the concerns or potential impacts of nanotechnology in engineered nanomaterials, and hence the need for responsible development and innovation. I'll also talk to you about a few recent approaches to ensure the responsible innovation of nanomaterials and a few different projects that I've been involved in. And so hopefully some of this will provide some inspiration or guidance on maybe what you could do in your own projects. We'll wrap up with some conclusions and next steps. Okay, so real quick, I won't go through everything, but as Reza said, I'm currently a senior research scholar at NC State University in the Genetic Engineering and Society Center. I'll be transitioning to an assistant professor position in environmental health and risk assessment starting in July. Before this, I was at RTI International, where I also was able to be a visiting scholar at Duke University for a year, an adjunct professor in Meredith College for a year, and obtained my PhD and a master's from the Technical University of Denmark, also having a natural science degrees as well from Michigan State University. So currently right now I work on a range of projects in GES Center, and the one that's most exciting I think right now is I'm currently the PI of the USDA NIFA grant that's looking at the societal implications and best practices for responsible innovation of nanotechnology, specifically in food and agriculture sectors. So this is a 2-year project. We're also working with our colleagues at RTI International on this work. I'm currently leading an initiative to grow the field of risk science in the GP area through funding from the Society for Risk Analysis. So if any of you or your colleagues are interested in becoming more involved in the chapter here, please feel free to reach out to me and I can provide some guidance. We're also doing some fun like meetup local events, which are really fun. You can meet people in the area. We recently closed out this project. We just completed a successful project that spanned the last 3 years, water sustainability through nanotechnology. Jacob Jones was the PI of this project, and I led the efforts to look at the environmental health and safety risks of nanotechnology used in water filtration and water treatment. And I'm also involved in the Research Triangle Nanotechnology Network, which is an NSF-funded grant, also led by Jacob Jones, and I'm working on some of the environmental health and safety risks and societal impacts and implications of nanomaterials. So that's what I've been working on now. I have a lot of different projects, and it's all really exciting because they kind of coalesce around the ideas of risk and responsible innovation. Okay, so I realize that many of your colleagues are experts in nanomaterials and nanoscience, but for those of you who are dialing in or listening in that are not so familiar with nanomaterials, I just wanted to give a brief background about what these materials are real quick, and feel free to jump in if I'm missing anything important that you think is worthwhile to include. So engineered nanomaterials are new materials that are innovated and engineered specifically at the nanoscale, often termed as between 0 and 100 nanometers, although there are some varying definitions by institution or organizations. And the reason why it's important to define and to describe some of these nanomaterials at such a small scale is that often by shrinking the size, it can actually have new functionalities or new and novel properties. So we have seen this in many cases. My favorite example to give is with gold. So at the bulk scale, gold does not react like with your skin. That's why we often have it with in jewelry applications. But by shrinking the size of gold at the nanometer, it can actually become very reactive. So this is just one of many examples where changing the size actually changes the different functional and physical chemical properties by doing so. And this is actually really exciting in some ways because we've seen a lot of different consumer applications and products that have capitalized on the new nanoscale material and their novel properties. So right now, according to the Nano database, there are over 3,000 consumer products on the market that could contain engineered nanomaterials. And this has led to a lot of really exciting, interesting new products and applications utilizing some of the lighter, stronger materials. I think of carbon nanotubes used in sporting equipment, tennis rackets, or bicycle frames. Also new electrical, magnetic, conductive properties. Nanomaterials are used in medicines or antimicrobial agents, and as well as environmental applications. So here on the right, you'll see this life straw that has carbon nanotubes in it to be used in some developing countries as a cost-effective way to have a clean drinking water. We also have zero-valent iron used in the bottom right to clean up environmental pollution, as well as flexible solar cells here. So there are a lot of really interesting applications that have been using engineered nanomaterials. So yeah, there are a lot of different materials. I think one estimate a few years ago was that there could potentially be over 50,000 different types of carbon nanotubes between single and multi-walled and all sorts of different functionalizations, and they're used in a wide range of products, everywhere from electronics to automotive, clothing, sporting goods, children's toys, food, et cetera, et cetera. So I can provide more information if you're interested on where to find more information on nanomaterials used in different consumer products. So the NNI, the National Nanotechnology Initiative, has been spearheading a lot of different work, of course, in this field, and they they have put together different reports. This was just from last year, showing a different array of different nanotechnology applications in aerospace, drinking water, computers, health monitors, food packaging, etc., etc. And as I mentioned, there are some consumer product databases, such as the Nano database here on the left, and you can search through this database to see which different consumer products could contain nanomaterials. I just searched for kids the other day. You can see like a kids nano T-shirt, sunscreen, pants, etc. And similarly, there's a database put together by the Center for Food Safety, and they have a lot of different products. I think close to maybe 2,000 different products that contain engineered nanomaterials. And you can go scroll through that and see see the different products. Okay, so, and we know that indeed, like, there's been a lot of funding behind nanotechnology and the development of nanomaterials. This is just looking at the U.S. alone for the budget over the years, and we had it looked like a budget spike around 2010, 2011, across different agencies. And overall, the NNI has put together 4 specific goals about how they want to grow the field of nanotechnology development. 1 is to advance a world-class nanotech research and development program. 2, foster the transfer of new technologies into products for commercial and public benefit. 3, develop and sustain educational resources and skilled workforce, etc. And 4, to support the responsible development of nanotechnology. And I'm going to talk to you mostly about goal number 4. So the point of me saying this is that there are different, goals, but one of them is to support the responsible development. And we also, when you look at the breakdown of funding from NNI over different program components, you can see that 40% is applied to foundational research, about 30% is to applications, devices, and systems. And if you look at this small sliver up here for environmental health and safety, about 5% of the budget has been going towards specifically understanding the environmental health and safety impacts of nanomaterials and nanotechnology, largely in light of this goal number 4, to support the responsible development. But some of the other foundational research could also go into goal number 4 as well, just to develop the basic metrology or analytical methods for detection, etc. In a recent, on NNI's website, they even said that the cumulative EHS, environmental health and safety investments through 2006 to 2015 have reached more than $1 billion. So there have been significant investments made to understand some of the environmental health and safety aspects of nanomaterials. And why is this important? Why are they going to put such a large emphasis behind the responsible development of nanomaterials? Well, it's because there's largely been a consensus that this needs to happen, that we need to have sustainable, responsible nanotechnology development. This is a part of the U.S. NNI's goal, as well as the European strategy for nanotechnology development. This is essentially a way to help guarantee the success of the overall technology, and also because we've had other experiences with other emerging technologies. Think of the whole GMO debates that have occurred, especially within Europe. So you had a technology that was developed, it had all these potential benefits, but yet it was not ultimately successful in some parts of the world because of largely social factors. So we did not want, or the nanotechnology community did not want to see a repeat of this. And so to help avoid some of the public backlash, the whole idea of responsible development of nanomaterials was put forward. This can also be related to things like green design, and right now it's there's a lot of focus on safe by design in Europe as well. Okay, so what does it mean to do responsible development of nanotechnology? What does this include exactly? So according to the NNI, this includes not only the
environmental health and safety aspects or implications, but also the consideration of ethical, legal, and societal implications as well. So according to the NNI, we should factor in EHS and LC considerations within the technology's development. And they said that in order really to, you understand the behavior of nanomaterials and couple this with LC considerations so that the public gains confidence and there's regulatory uncertainty. So ultimately you can bring nanotechnology products to the market. So that's been the underlying motivation for doing this type of research. And I think I'm spending a little bit of extra time really honing this in because I'm going to talk to you about some examples of what this means in some projects, but we really need to remember why we're doing this and what's the ultimate goal of doing this. Okay, according to NNI's website, what they've included under their environmental health and safety aspects, and you can look more if you're interested in their on their website as well, but they have 6 core research areas. So nanomaterial measurement infrastructure, exposure assessment, human health and environmental health, probably like toxicity, ecotoxicity work, as well as wrapping it up into a risk assessment and risk management methods and informatics and modeling work. And they give some examples of different EPA-funded work as well that have supported these missions. I've primarily worked within risk assessment and risk management methods throughout my research career. Okay, in terms of the LC considerations, the NNI they're pointing to two centers, and I think this last one may be phased out now, but there's this one center still ongoing at ASU that is looking at more of the societal implications of nanotechnology work. And so if you're interested in more information on what's being done, I would point you towards this center as well. Okay, so before we start going into some examples of some different projects looking at the responsible development of nanomaterials, I just wanted to frame some things within a risk assessment component. Because in order to responsibly innovate or develop, you actually have to understand the risk side of it. So it's kind of two sides of the same coin. Okay, so for those of you not familiar with what risk assessment is, it's actually there's a structured way of thinking about risk and doing risk assessments based on the ultimate product that you're interested in investigating. So the current approach for nanomaterial risk assessment is really based on the chemical risk assessment paradigm, and it's been opened up to a larger field of risk analysis, which I'll get to later in the presentation. But risk itself is generally defined as a combination of both the exposure and the effect in order to generate a risk. So, and essentially, this helps answer the questions of how probable is it that a health or environmental agent will suffer an adverse consequence from in a given scenario. So we can ask questions like, what can go wrong? How likely is it? If it happens, what are the consequences? And right now we're kind of playing around with these questions, when we think about the coronavirus in terms of risks. Like, so if I get it, how hazardous is it to my health? How can I not get it? How can I limit my exposure? So we're already seeing this play out this week, especially. And then the risk assessment is really, as I said, like a structured method for doing this, and the output is a quantification of the likelihood of risk. And often risk assessment is a component within a larger risk analysis framework that considers risk management and risk communication. So when I tell you about some of the potential risks with nanomaterials, you have to keep it in mind that this is part of overall management and communication paradigm that needs to be applied. So I'll probably come back to this risk analysis framework in a few slides. Okay. And I'll also just wanted to say quickly that a risk assessment and risk management are coming together to make a decision, especially a regulatory decision, about risk, and that risk-based decisions are not based on science alone, and we really need to remember that. This is important conversation when scientists are sometimes using this thing called the deficit model, where they think if only we understood the risk, and if everybody understood the risk, then everything will be okay. But that's not necessarily the case. That often there's other factors that go into decision-making cases, including some socioeconomic or political decisions. Okay, so getting back to the world of nanomaterials, as I mentioned, there are some databases that show nanomaterials used in consumer products as well as food. This is put together by the Center for Food Safety, and you can go in. I can give you the link if you can't find it, but they have this database, and you can see the different types of nanomaterials that are being used in food and food supplements. And it looks like titanium dioxide and silver are big players here, and some nano-encapsulation of various nanomaterials is also another well-used application. So there are a range of different materials or elements that are used in food, but these are some of the main players according to the site. And across the different categories, we have a large component of food supplements and additives that are claiming to contain nanomaterials. These are things like nano-silver supplements, colloidal silver, foods believed to contain nanomaterials, and this could be because of a current food additive that's already used at the bulk scale. We know that it's now being used at the nanoscale as well, even though it may not be labeled as such in the U.S. And we also see other product categories such as baby and infant products, filtration and bottle products, and packaging, etc. So we actually did some work on nanomaterials in food a few years ago, and I'll point you to our paper in the Journal of Food Protection, where we listed out different examples of nano food applications, and the types of nanomaterials used, their use, their function, where they could be found, etc. So we found that actually synthetic amorphous silica, which is a current food additive, was one of the main players, as well as titanium dioxide, silver, as I mentioned before. So I can point you back towards that article if you're interested in reading it. In another paper, we looked at some analytical and detection challenges with nanomaterials in food, and this is coming out of this paper, but we are looking at here some of the fate and transformation. So if you have different nanomaterials used in different foods, for example, how does this impact your health, or what happens after you actually eat these different nanomaterials in different foods? So we know for sure that the nanomaterial is not going to stay the pristine nanomaterial, that there's going to be a lot of changes that occur both in your mouth as well as in your digestive tract. So the materials may aggregate or agglomerate, they may change their surface properties, the pH can change, et cetera, et cetera. So we know that what starts off as a pristine nanomaterial doesn't end up always staying that pristine material as it travels throughout your gut. We also know that there can be some potential effects that have been noted from the literature, from the toxicity literature, such as systematic effects, such as pulmonary, cardiac, reproductive, renal, cellular effects, et cetera, et cetera. And there's also some speculations that nanomaterials could impact or alter the microbiome community in your gut. And we know that those communities are really responsible for a lot of important functions, such as nutrient uptake, immune functions, etc. So there's still a lot of work being done. It's an active research field, but we do know that the nanomaterial that you would ingest will change itself, as well as potentially lead to some impacts within the human body. And actually, this touches on the whole field of nanotoxicology that was born in the early 2000s, that since there was a growing recognition that engineered nanomaterials could have toxicological responses on the human body, there became actually a new field of nanotoxicology. And in this one paper, there's several, but I like this figure that shows kind of some different effects or toxicity that nanoparticles can cause, both at the molecular, cellular, but also at the organ level as well. So we have the formation of reactive oxygen species. You can have membrane disturbance, you can have protein binding. At the cell level, you can have things like macrophage overload, antibody formation, inflammation, etc. And then, as I said, some organ level. So there is a whole body of literature out there in nanotoxicology pointing towards some potential impacts on the human body from exposure to different nanomaterials. And in responsiveness, because it's still a growing field and we don't have all the answers yet, in the European Union, they decided to start labeling foods containing engineered nanomaterials as of the end of 2014. So if you buy a nano food product, so let's take gum as an example. Gum would contain some titanium dioxide. So if it contains nano titanium dioxide, on the package of the gum, there should be in the label, titanium dioxide parentheses nano, just as a way to serve as an information providing mechanism, as it says here, to give consumers better access to clear, comprehensive, and reliable food information. Okay, so this is just, example of, we have different nanomaterials used in consumer products, including food, and there's a lot of evolving science on the impacts maybe of this food on your body. And while we're still getting all the answers to those toxicological impacts, labeling has occurred in some parts of the world. We have another paper about some of the international implications. If you're interested, I have the full paper citation at the end of the presentation. Okay, back to risk assessment. Then health and risk assessments are still in development. As I mentioned earlier, there's both the exposure and the hazard components that make up a risk. And these risk assessments are done on a case-by-case basis, which can be very timely, very time and resource expensive. And in fact, in the case of foods, we have other challenges as well for just detecting nanomaterials in foods. Things like separating or extracting nanomaterials from the food matrix, distinguishing nanomaterials from naturally occurring or incidental nanoscale materials, detecting organic nanomaterials, and as well as developing standardized approaches and tools. The FDA formed a nanotech task force about 15 years ago, but there are no hard rules or regulations regarding nanomaterials in the U.S. at this time. They have produced, by FDA, they have produced some guidance documents. If you're interested in wondering whether FDA-regulated product involves nano, if you want guidance for assessing the effects or safety and use of nano materials in food for animals. So you can search at their website if you'd like more information there. And in fact, because of all of this, I'm just giving you kind of a snapshot of some of the major aspects with nano in foods. Because of all of this discussion and kind of some uncertainties, for example, France has banned, so in addition to the labeling, France has banned the use of titanium dioxide in food completely as of January this year. And this was largely out of some studies looking at pre-tumorous damage in the colon of rats fed with TiO2, titanium dioxide nanoparticles. So because of some of this evolving research with nanoparticles used as food additives, France has decided to ban all of TiO2. So this has actually caused a lot of discussion and a little bit of uproar about, about the safety and some toxicity studies regarding TiO2 nanoparticles. So those are on the health side. I will just mention quickly on the environmental side, some work that's been done. So similar to the field of nanotoxicology, we also had a similar field that evolved in the early 2000s of nano-ecotoxicology. Here's one paper that's specifically devoted to nanomaterial impacts on environmental organisms. And we worked on a paper about 10 years ago looking at some of the impacts of nanoscale zero-valent iron particles used to clean up the environment. And across our paper, we looked at different studies that investigated ecotoxicity impacts of NZVI nanoparticles. And we also published a book chapter as well. And to make the long story short, we concluded that while NZVI has potential as a competitive in situ environmental remediation technique, it doesn't look like it's been developed and used in the most sustainable manner. And this is because most of the research has been on the ecotoxicity or toxicity, but there has not been a lot of research still on the long-term issues of exposure, bioaccumulation, persistency, and moreover, there's been very limited work on the social ethical side as well as public participation. So here's another example where there's a lot of benefits, a lot of it could be a very cost competitive environmental remediation technique, but it could have been developed in a more sustainable, responsible way had there been more long-term studies or social and ethical work. I'm going to skip that. Okay, so coming back to the whole field of nanomaterial risk assessment and risk analysis. We started off in the early 2000s with with wanting to develop nanomaterials in a responsible, sustainable way to basically get the benefits while minimizing risk. And so there's been a lot of different approaches that have occurred since this time. Most of it, initially we started off applying the chemical risk assessment framework to nanomaterials. And indeed, there's been a lot of different work. So remember I told you about exposure and hazard being the two parameters coming together to make a risk. So here's some exposure down here and hazard to get to the risk assessment part of it. So we really have made some amazing, enormous strides with understanding the risks of a lot of different nanomaterials. And we really should be proud of all the accomplishments that we have made. But at the same time, today, as of early 2020, there still remains to be a lot of uncertainty with being able to draw concrete conclusions whether different nanomaterials are pose a risk to the health or to the environment. There's a lot of things that we still don't know. And regulations are really struggling to keep pace with the new science and the new data. As I showed you earlier, there are over 3,000 different consumer products that contain engineered nanomaterials on the market right now. And yet we still don't fully understand their impacts on human health or the environment. And at the same time, decision makers, including regulators, need to make a decision about those today. So we are still in a tricky spot. We've really moved from trying to apply the traditional risk assessment approach for nanomaterials more towards a risk governance and decision-making approach today. So after trying to apply chemical risk assessment for nanomaterials, there have been other frameworks that have proposed and developed, and we published a study in 2012 that reviewed some of these. And then since this time, there's been other methods that have been developed to try to understand some of the risks of nanomaterials, but it's a little bit like comparing apples and oranges and bananas all together. So we were really struggling being able to compare the same tool with the same tested application. So in another paper that we published in 2018, we actually did that. We compared the outputs of 3 risk screening tools together. And that had been the first evaluation of that kind that had been published in the literature. And right now we see that there's a lot of different approaches, a lot of frameworks. It's still kind of, evolving in terms of the best risk assessment strategies. There's no gold standard for conducting nano risk assessments today. There's also different international regulatory requirements. In EU, they have REACH, which is different. They have different requirements than what we're doing here in the US at the moment. And there's increasing reliance on more risk governance or decision-making frameworks in the near term that don't rely just on a quantitative risk assessment output. We almost need like a roadmap to select the right tool at this point. We continue to need more tool testing and validation that builds off some of our early work. I was a part of a European project called Calibrate that was working on this, and then Calibrate is followed on by 3 separate risk governance projects in the European Union right now that have just got started. In our analysis, we applied 3 different tools, and to make a long story short, we thought that instead of you don't always need to just use one. You could use them together, basically, when you're not sure, because the tools are still new and quite unsure with which tool would be the best in certain situations. So you can try a tiered approach if needed. Okay, at the same time, so this is the path that we've seen with nanomaterials. And we're still not there yet. We still have a long ways to go in order to really develop a quantitative risk assessment. But at the same time, we've seen the other emerging technologies have also arisen. Things like advanced materials, synthetic biology, artificial intelligence, machine learning, 3D printing, climate engineering technologies, et cetera, et cetera. And with my involvement in some of these other technologies, I was really starting to see this picture about the need for a larger discussion on what it means to do risk assessment and risk analysis with emerging technologies in the early stage, so that maybe we could learn from some of the lessons that we've gone through with nanomaterial risk analysis, that we can learn from these as we go forward with other emerging technologies. And out of this vision, we published a paper late last year in Nature Nanotechnology on just this, the best practices from nano risk analysis that could be relevant for other emerging technologies. And that had really been like a compilation of ideas and thoughts from the last 15 years. I would recommend taking a look. It's a really short article. But I can tell you more briefly about some of the main take-home messages that we have from this work, and I hope that I can share this with you, and you could also reflect on your work in nanoscience or advanced materials as well. So one is that we really need to promote research that's tailored for regulatory decision-making, because normally what happens is that you have an emerging field, and this is published by Linkoff et al. Several years ago. You have an emerging field, and then there's the data, the environmental health and safety data that's produced afterwards, and then decisions are made. But what we really need to do is have a more tailored research program for regulatory decision making, right up there with the emerging technology and innovation. This will help us reduce this lag time. And in addition to that, we really need to set more realistic time, cost, and complexity estimates to develop risk analysis, because now after 15 years, we've spent a lot of money, like I showed you earlier. Estimate was over $1 billion in EHS studies, and we still don't have the answers. And so we need to be, I think, more realistic about how long it's going to take in the cost of developing some of the environmental health and safety data. And also, this couples back with the idea of actually promoting regulatory decision-making as a research program, just like in a new innovation. We also need to develop strategies to deal with uncertainties in risk analysis and decision-making, because, as you know, science is not always so clear and direct. Sometimes when you answer one point, you end up realizing factors that you had not known about before. Or, just like the game of whack-a-mole, you whack one down and two more pop up, like, because science is complex, and there's things that we didn't fully understand. And so you start to realize that there's more complexity than meets the eye. So just, for example, there's many examples, but all nanomaterials or all types of one type of nanoparticle does not necessarily behave the same. So, you can have different toxicological responses based on the methodology used in the toxicity assay. And there's many other examples where there's a lot more complexity than meets the eye originally. So we need to come up with better strategies to deal with these uncertainties in the beginning. And also within emerging fields, we really need to somehow develop mechanisms to share risk data early on while also protecting privacy, confidentiality, and proprietary information. This will help us be able to better understand where the state of the science is early on, and harmonize that later. And last but not least is the need for critically evaluating and selecting the best fit-for-purpose tools for risk analysis. So in the case of nanomaterial risk analysis and risk assessment, we set off using the chemical risk assessment framework, thinking that if only we can complete this quantitative chemical risk assessment framework, then we'll have all the answers and then we'll know what to do. But the problem is that's taking a long time and it's a lot more expensive than we thought it may be. And maybe other tools could help us in the meantime. So for example, if you're developing a new material for use in a different product, instead of needing the results from a risk assessment, do you need maybe an alternatives assessment? Do you need to select which of the 5 nanomaterials that you're working with could be the best? Or is it that you need help with another decision-making need? Is it something that multi-criteria decision analysis could do? So there are different tools in the toolbox. Not everything has to be decided from a quantitative risk assessment in the near term. Ultimately, we will need to get that quantitative information, but in the near term, there could be other tools in the toolbox that could be helpful. So I'll skip over this a little bit. So this is just from one paper that I was showing you earlier, that there were different tools for screening nanomaterial for their toxicological and ecotoxicological hazards and exposure potentials. And right now, like as I mentioned before, they're not apples and it's not comparing apples to apples, it's comparing apples and oranges together. And so what we came out of this paper was that, again, there's more tools in the toolbox and maybe we can use them together. And that's what we did. And as I also mentioned, folks are taking some of these tools in the toolboxes and testing them and validating them. And this is where we're at today, is that it continues to be part of this. So I was a part of this Calibrate research project that was really about nanomaterial risk governance. And it closed, it finished just in December of 2019. And now 3 other projects are being developed. So I've been talking to you a lot about risk, and now I'm leading a project about responsible innovation. And we just started this the summer of 2019. It's a 2-year project. And the idea of this project is to really identify and describe cases of responsible research and innovation in nanomaterials used in agriculture and foods, to look at some of the incentives and barriers for doing responsible innovation, capturing stakeholder perceptions and concerns, and really to capture some of these lessons learned and best practices that could be applicable to other food and agriculture technologies. So this has been a really fun project because I can hear directly from company representatives and those in academia about what it means to them to responsibly innovate. Are they just thinking about environmental health and safety? Are there other larger considerations that they factor into? What are some barriers to, even if they want to responsibly innovate, what are some barriers to getting that done? And so if you're interested in more information on this project, I'd be happy to share with you what we're doing. Jennifer Kuzma at NC State is a co-PI, and as I mentioned, we are working with partners at RTI International and a private consultant, Christine Hendren, as well. Okay, so to conclude and talk about some next steps. So I showed you a wide range of different concepts today, and it may be a little bit different than what you're normally talking about. But as you know, engineered nanomaterials are used in a wide range of products and applications. There has been a lot of research on environmental health and safety, as well as ethical, legal, social implications since the mid-2000s. But it's still unclear if and how the research findings have really been incorporated into innovation today, especially since risk assessment and risk analysis for nanomaterials are still evolving, and there's no gold standard to the approaches used. And I wanted to show you a snapshot of a few nano innovation efforts that I've been involved in, such as the use of nanomaterials in food, environmental remediation, water treatment technologies, as well as my involvement in nanomaterial risk governance and responsible research and innovation within food and agriculture sectors. So we've learned with some of our interdisciplinary work over the past 15 years that we really need to have harmonized approaches to developing responsible innovation of a new emerging technology. You really do need this multi-stakeholder collaboration involved, because that's the way that you can understand all sides of the puzzle. And that this is a really an evolving risk, that the field of risk science is evolving, the field of nanomaterial risk analysis is evolving, similar to other emerging technologies. And so as many of you perhaps maybe nanoscientists or nanomaterial developers or innovators, I will put it back on you. You can ask yourself, what could I be doing? Am I taking into account environmental health and safety considerations with my own research? Am I taking into account ethical, legal, societal implications? What else could I be doing? Or should I partner up with other people? So we at NC State would be happy to partner up with you, at least just to have a conversation about what you could do in order to ensure the responsible development of nanomaterials or advanced materials or whatever you're working on. I'll also conclude with saying that if you're interested in concepts about risk, which really combines, I would say, quantitative data with social values, then please feel free to reach out to me. You can come to some of our informal meetups with the Society for Risk Analysis. You can give a talk, or we can share with you some of the fundamental science behind the field of risk, because there is a lot to learn here that can be applied in different fields. So feel free to reach out to me. And I'd like to acknowledge the funding, my funding sources for all the work that I've shared with you today. So with this, I thank you for your time and attention, and be happy to answer any questions that you may have.
All right, thank you. So we don't have many people online right now, so if you have questions, please submit them through the chat. I know that we had some problem earlier when we started the broadcast with the audio. We are this is the first time, so we're gonna fix that hopefully for the next one. I checked the one that was recorded. Right, this I think it was recorded, and that seems to be so. I don't think that there was a big problem. I could hear some part of the conversation very well. But that being said, I think I was not also mute, so that might have participated in the noise in the background. So, but I guess we can check that and make sure that the quality of the video can be increased, or the audio could be increased. So if you have questions, please ask online. And so let me start with having a question regarding So you referred to development of some strategies to mitigate risk and talk about what could be done to resolve the problems that may come from the applications of the nanomaterials. One thing that comes to my mind is that is it too late or is it not? Because we know that nanotechnology was existing for a long time. It's beyond 20 years now that we are talking about nanotechnology. So do you think it's too late? Or, I mean, of course, we start, so any time is the right time. But my question is it too late? And if it is too late, or if you think that we could do much better if we started earlier, do you think that other fields can benefit from that? And so I would like to hear about this.
Okay.
Yeah.
Okay, what do you mean? Do I think it's too late? Too late for what?
Too late for starting thinking about what the
Impacts
for this should be, like what should and should not be done.
Okay, in terms of what? In terms of addressing risk, in terms of responsibly innovating, in terms of communicating to the public?
Yes, all of that basically.
All of the above, okay. What's the government's responsibility?
Yeah.
Okay.
Because at the end, ultimately, the government would be the entity that enforces some of these regulations. So if it is
Sure.
like 20 years after the field started and you have produced, or as a community, we have produced so much things that can destroy the environment, for example,
Yeah.
it could be done better. I'm not saying that, but I'm just asking if you think that that would be something.
I understand. Okay. So the number one thing that comes to my mind is to incorporate these broader issues of responsible research and development into innovation cycles, into early R&D research, so that everybody is thinking about this from day one. Not just, I've got this new thing, it's going to be so cool, maybe I can have patents or papers, but also think about what are potential environmental, health, safety, ethical, social considerations. I know not everybody can do everything. I'm not saying that, but just that have those conversations in the beginning.
Yeah.
Or couple up, partner with me, partner with somebody else that can help ask those questions in the beginning. Because what we don't want to do is to develop something that later causes a problem. I'm really about prevention rather than dealing with it after the fact.
Yeah.
The problem, our systems are just not set up. Our systems right now are not set up for this. Our promotion, or whatever, our whole infrastructure and systems are very, let's see if it works, and then we'll ask questions later. But we know time and time again that that's not probably the most effective, actually cost effective, because it's going to be way costlier to fix it at the end of the day. It's a very complex discussion. There's a lot of things about who's taking the risk and who's bearing the risk.
Yeah.
Because often the risk takers are not the ones that have to deal with the mess afterwards. So in all situations. So I think it's a very complex conversation. I would personally like to see more work done in the beginning of innovation stages, even having the conversation, Rarely am I asked, I guess I've given maybe 5 talks in the last 15 years to nanoscientists. 5 talks. How many I've given, lots of talks to nano safety people. But so anyway, it would be nice if we could have that conversation earlier. But I understand funding is becoming scarcer and scarcer. So this is, some of the challenges, when you only have a finite pot of money for your product, it's risky for you then to take a chunk of that and devote towards, understanding the impacts, when you just need to get it going. So I think it's a whole way of rethinking about how we do R&D, in my perspective.
So what fields do you think right now need that considerations of risk management, and so what new fields I'm asking about
Mm-hmm.
fields that you think would be benefiting from communicating with you and getting you involved as they are being developed or
Yeah.
started.
Well, I don't have the ultimate, correct answer, but the first thing that comes to my mind is like the most risky field, something that would have, a wide exposure and severe potential impacts from exposure. So I'm thinking, cases where you have like a higher degree of risk, then I think that's especially where you would need to factor in these conversations. And it doesn't necessarily just mean environmental health and safety risk. It also could be social and ethical risks as well. I think directly, using the nanomaterial lessons learned, it would be great if we could transfer this to the field of advanced materials, because that just is, the next generation of nanomaterials. So advanced materials that are not just on the nanoscale, but maybe a little bit larger. What could we learn from this? Apply there. So that would be one thing. I have been working with climate engineering technologies as well, and there's definitely a need for responsible research and innovation in that field. And often I will say, like, there's often not clear answers, and there may be a lot of different trade-offs. So protecting health may be traded off with, I don't know, protecting the environment or something like this. So, there's going to be a lot of decision making and combination of different factors when you make those decisions.
Yeah, I mean, as you were talking about this, I was just thinking about like the IT, revolution. Suddenly, something happened without really thinking about the consequences, and now we see some of that. And of course, everyone, I guess, is aware of what the problems are. But we could definitely do better. So right now, I think we consider some of the issues as big challenges and problems, like if people text and drive, for example, right? Which is a very simple, side effect, I would say. There are much bigger problems, like political and environmental, and everything is affected with that. So having those conversations, I think, benefits us a lot, especially when something becomes dominant in the society. Like if we have a particle that would come into our houses and we use them like every day, that would be a very important thing to first talk about.
Right.
Yeah.
Also, I'm going to go back to a slide that I skipped earlier, because it's what you're talking about, like the framing and the whole grand scheme of things. Yeah. Like it's also important to remember, that just like some people have a tendency of thinking if it's natural, then somehow it's like less risky, right? Than if it's a technological thing. So, and there's all sorts of different factors that go into risk perception.
Yeah.
There, like we were talking about, like the flu killing more people than the coronavirus, and so, but it's about this perception. If it's new, it's emerging, you don't have control over it. It's not as familiar, so people's perceptions change as well. So we know that. Yeah, but here from NIH it says chemical toxicity is a sliding scale. It's not black and white. This was just comparing like chemicals to naturally occurring substances, but it's about like this risk perception that some folks have. So, myself included, of course. And so, yeah, it's an interesting conversation, when you talk about texting and driving, or autonomous vehicles, or driving versus flying, you have the emotion and some of the statistics, and sometimes you have to use different, like with some people, the statistics are important and they respond to it and they can alter their behavior, but other folks, statistics aren't the thing that they are going to be motivated by. It's more an emotional response. And so we are human beings that respond slightly irrationally at times.
So following up that, I'm curious of knowing. So there is a distance between public and scientists. We have this problem as scientists. I would say we usually have this problem of communicating with public. Like when we're talking about one of the innovations in our lab, like when I'm talking about an innovation in my lab, right? I talk and I bore the other side, but I don't give them the main message usually. And then they get scared at the end of the discussions. And I'm talking about a very simple conversation between scientists and the public. So what do you suggest we do as scientists to overcome that problem? And there is a fear that when we're talking about things, and when especially as human being, when we don't know much about a thing and someone talks about it and it's a completely new thing, maybe it will be very, very good development, but it's a new thing. So we as human, we don't really respond well to new things, changes, and it's really scary. And especially when we don't know much about it, it would be even scarier.
So as scientists, I would really recommend that you either get training in communication, science communication, or risk communication, or you partner up with a communication expert. There are people at NC State, for example, and maybe at your place as well, that they have a PhD in communication or risk communication, so there are skills that you use. There are things that you do in order to perfect your communication. Actually, wording and context really matter, and so you have to be very careful in the words that you choose, who presents the information. I mean, so I would say, partner up with an expert if you don't want to be the expert yourself. And another thing we really know is that the public trusts scientists probably the most, academic scientists the most. Trust is very low in government and industry right now. So, it's coming from you, which is good. Messaging is important. You can get help with it, and don't try to hide behind something. Like people, if they sense that you're hiding behind or not telling them the truth or telling all of the truth, this will lead to a lack of trust. So try to be as open and as transparent as you can be, working with a risk communicator expert probably. And also, people are better with uncertainty than I think that we give them credit for. So you can say that you don't have all the answers, and that you don't know and you're working on it. So I would say be as proactive as you can, and you can engage with the public. You can set up focus groups, or you can invite, have an open house. You can really try to gain, access to the public by being open. And you can listen, you can have different formats for listening about some of the concerns that folks have. In the case of GMOs, it was really not, and I'm not a GMO expert, but from what I've understood, it's not a case of the hard risk, whether it really causes risk to my human body or something. It's really about some social concerns, and that maybe we just don't want it. And who's benefiting? Is it companies benefiting and they're pushing it on me and I don't have control? So it's not really about the actual risk. It's about the perceived risk and about factors of trust and control. So this is really a lesson that, was learned, is that these social and ethical considerations are really important to consider. And that scientists, like some of the folks that are developing it, they often don't really realize how important these social or ethical, even moral concerns really are to making something a success. We do see that there's a little bit of difference between nano and GMO or genetically edited crops, so it's not going to be exactly the same, but there seems to be like less backlash, I would say, on nano than there has been shown with GM. So
what do you think about synthetic biology? Like, do you hear the messaging is improving regarding the synthetic biology, given that synthetic biology is a new field? It's like probably
actually, I don't know.
Years ago of nanotechnology.
Right. I don't know. I have not really worked in the synbio space. So I know that my colleague Chris Cummings just produced a book. Jennifer is also a co-author on some of the chapters, and so, or I think she's a co-author on the whole book. And so I can send you the link to the book if you're interested.
Yeah, thank you. Yeah,
yeah,
so we have one question from the viewers online, and I'm not 100% sure that you can respond to this question, but I'll read it to you. So, are you seeing newer tools being used, like Raman hyper spectral image system and aerosol capture devices for characterization of nanomaterials for assessing worker exposure in semiconductor fabs?
If I understood, because you were kind of cutting out, then you said, am I seeing the use of these new spectroscopy tools being used to help understand exposures?
Yes.
Okay. Yes, for sure. This is definitely used in nanomaterials and foods. They're trying to get these the ability to detect different types of nanomaterials in complex food matrices, but right now I think the tool development is still underway. Like, we still don't have a silver bullet for everything. You have to use different types of tools for different nanomaterials in food and maybe other environmental matrices as well. So yes, and I think it's still in development. I'm not an analytical tool specialist myself.
Yes.
But I know it's definitely still an evolving field, and it's important. I think also another thing is like what sampling approaches, right? So if how do you sample properly? I think that's something. It's not just that's why I have the standardized tools and approaches. Like you have the tool, but then you also have the protocols for using the tool that I think are still being evolved in different matrices.
So knowing our student body, I guess the question is more about probably do you see companies, industries take these precautions, these things serious and analyze them? Do they use them right now?
With the companies that we have had as participants in our study so far, they've been pretty small to medium-sized companies, so they may not be representative of the larger companies. So some of the results that we find is that these small to medium-sized companies are either partnering with the university, or trying to get help in some way for understanding the potential impacts of their nanomaterial used, but I don't think that they're necessarily relying on detection, like new analytical detection techniques themselves. I wonder if it's the same for larger companies. I don't know. Nobody's responded from a larger company.
Yeah, that's the problem. So regarding that, do you see big differences between Europe and US? You have worked in both environments.
Well, the biggest difference is just like the regulatory standard, the regulatory needs. Like I think that starting January of this year, there's now nano-specific reach requirements, which will require, right, analytical tools to be used for detection purposes. So I just, the last time I was involved in the EU project, I know that they were still like, there's an ongoing discussion about what does this really mean? And I think that I saw a couple presentations like, this is what we're supposed to do, have nano-specific reach requirements, but can we really do it? And what are the challenges to doing it? And that's the last I've heard. I haven't heard of like, I don't know, a success story yet, but maybe it exists. So I think, yeah, the biggest thing is regulatory requirements, and probably funding levels right now for this type of work. I'm just not seeing the large scale, centers that are being awarded right now in the US.
Yeah. So is it a new thing, or do you think it was existing and now removed, or is it like it continuously not really existing?
That's a good question. I mean, just in my own personal experience, I feel like the funding is kind of going down a little bit for nano environmental health and safety work, but maybe it's being spread out into different fields. Like maybe it's just being more application driven now. And this is something, I don't know, I think I almost would need to do like a little bit of digging or research to really understand like what's going on. We still have things, like we have these missions and visions, and we have some centers, and we have some work being done, but I'm not sure on the level of effort. It's just in my